In question B, we're assuming train B is unmanned. They're coming constant speed this way. So what's the equation of motion for train B? X final train B is X initial train B plus V initial train B T plus half AT squared. But if they're unmanned and their acceleration is 0, so this is 0, so you basically have X initial, V initial, T. And you don't even call it V initial because the velocity is constant, so you just put VBT. So the equation for the train B, 260 minus, what was the initial velocity of train B? 58, and it's gonna stay 58, but it's negative 58. Okay? Now we want to know what should the acceleration of train A be so that they barely avoid a collision. So we have the equation for train A. We have V initial train A T plus half AT squared. So you have V initial is going to be 44T. Now we know that the acceleration is going to be negative, but we just don't know its magnitude. So what we could do is put here A is negative A. So we just get negative A over 2T squared. And then once we solve A, that will tell us what the magnitude of A is, because we know that they have to decelerate, right? So what do we want to do? Well, we want to set these two equations equal to each other and solve for T. But you might say, how can we solve for T if we don't know what A is? Well, here's what the approach that I'm going to do. Okay, think about it graphically. Okay, this is X of T. What's the equation for the position of train B as a function of time? Train B is initially 260, and then they're coming toward you, right? So it's a linear equation like that. And since they're not accelerating, it's a constant equation. The slope of this equation is what? Negative 58. Equation for train A's position. Train A starts at the origin, but they decelerate and they want to avoid the collision, right? So their equation is something like a parabola. So it looks something like this, like that. Now, if it was like that, what would it be? That would mean it goes like this, like this, like this, and then this one stops and turns around, and they never even touch. You see, the closest distance that they get, is somewhere over here. You see the distance, the vertical distance? That means they come like this, and then this one stops, and then starts returning. So this is the best scenario that can happen. That means they never touch each other. What if the graph looks like this? You see? Then it looks like this one's coming. You decelerate, but you don't decelerate fast enough. You go like that, boom, there you collide. You see? You collide while you're moving. What's your velocity when you're moving? It's the slope of the tangent line, you see? If you take the slope of this, whatever slope of that is, then that's your velocity at the instant that you hit the other train. So that you don't want that to happen. So what's the best case scenario? What do you want to happen? Okay? You want something like this to take place. Like this. And if you want to barely avoid the collision, the graph is going to look like this. Okay? That means you will basically barely touch each other. You see? So you're going to go like this, stop, turn around, and at the instant that you're moving at the same velocity, you see this, the velocity of this is negative 58, right? This guy, that's the tangent line of this graph will also be negative 58. So at the instant that you're both moving at negative 58, you will tap each other. And then after that, the velocity of this train will be even faster, right? So one approach to this problem is to say, set these two equal to each other, this equation and this equation, and force the equation to have only one answer. You see, one answer for where they are equal, okay? So basically you say 44t minus a t squared over 2 is equal to 260 minus 58t plus 260. What's the general equation? What's the general answer for this? So remember, the quadratic equation is x equals negative b plus minus square root of b squared minus 4ac over 2a, right? If I want a quadratic equation to have only one solution, right? Why do I want it to have only one solution? Because I want the two graphs to touch each other only once, not twice. Twice would mean a collision happens, right? For this, we want the quantity under the radical, this is called the discriminant, we want that to be equal to 0. If that's 0, then there's only one solution, negative b over 2a, right? So b squared minus 4ac, we want it to equal 0. So what is my b in this case? b is 102, right? So 102 squared minus 4. What's my a? A is whatever is in front of the t squared, the coefficient of t squared, which is a over 2, right? So that's my a, is a over 2. What's my c? My c is 260. Okay? That will tell us what's your minimum acceleration so that you barely avoid a collision, right? So we have here 102 squared is equal to, this is goes into there twice, 520. 520a. Okay, so let's calculate that per second squared. But remember, we knew that the acceleration has to be negative, and we just already put the negative. So our answer should be negative 20. That means they're gonna decelerate, right? So our final answer is a equals negative 20 meters per second squared. That's a very fast deceleration, okay? In order to turn around, stop, turn around, and then go at the same velocity that the other train is going. What is another approach to solving this? Well, notice here that they are both going at the same velocity at that time, right? So here's one way we can say. We can say velocity of train A equals initial velocity of train A minus AT, and we want the velocity of train A to be equal to the velocity of train B, which is what? Negative 58. So this is negative 58. This one is 44. Okay, so now we have, this one goes over here, we have 102 is equal to AT, therefore the product of A and T must equal to 102. Now from there what we can do, we can say at that point, the two x's are equal to each other, right? X final of train A equals 44t minus a over 2t squared, right? So what you can do is do some substitution. You can say this one, a is equal to 102 over t. Take that and put it into here so that you get rid of the variable a. You have only one unknown t. So you can say this is 44t minus t squared over 2. T squared over 2. A is equal to 102 over t. You substitute it there. T and the t cancel and you get what? Okay, so this reduces to what? 44t minus 51t. So that's x final A equals 44t minus 51t. X final A is equal to 44 minus 51. That's equal to negative 7t. That means when the collision happened at a certain time, the final position of train A is actually negative. So in actuality, this picture should look more like this. Goes like this, goes like this. Okay, and this one goes, stops, quickly turns around, establish a velocity, and then right there. So at the point where they are barely intersecting, you are below the x-axis. That means It's wherever the original position was, it's gone, it's come back, it's now to the left of that, and then now they're going at the same velocity and they barely touch each other once, right? The slope of this is negative 58, and the slope of that is also negative 58. So now I take that and I set it equal to this, because I know when the collision happens, they have the same x position, right? Negative 7t equals 260 minus 58t. And then you take that over here, and then you divide that. 260 divided by 51. Okay, you get t is equal to 5.098 seconds. So that's how long it will take the collision to happen. Then you will put that back into this equation. A is equal to 102 over 5.098. 102 divided by the answer, and you get 20.007, right? And then, of course, the answer is the negative of that. So same answer, but we're looking at it differently. Instead of forcing one solution only, we're saying at the point that they intersect, they need to also have the same velocity, okay? So that's the approach that we do for question B. Now, how about question C? What's going on there?